Hello everyone, my name is Sudheer Kumar, working as an assistant professor of mathematics, MLR Institute of Technology. Today's lecture we are going to see definition of eigenvalues and eigenvectors and few properties of eigenvalues. Let us see the definition of eigenvalues. Let capital A is any square matrix and lambda is any scalar such that there exists a non-zero vector V such that AV is equal to lambda V. Then we say that this V is a non-zero vector and the lambda is a scalar which is called as eigenvalue of the matrix capital A. So eigenvalues are found by solving the characteristic equation. This is determinant of A minus lambda I equal to 0. This equation is called as characteristic equation, for which we find the eigenvalues. And A is the identity matrix of the same size A. If A is a 3 by 3 matrix, we consider identity matrix I3. So determinant denotes the determinant. By using this equation, which is called as characteristic equation, we find the eigenvalues which are denoted with lambda 1, lambda 2, lambda 3. And the corresponding eigenvectors are denoted with V. That is one eigenvector. Now let us see eigenvector. An eigenvector of a matrix capital A corresponding to eigenvalue lambda is a non-zero vector. Eigenvectors are always non-zero. There won't be any zero vectors. So non-zero vector V such that which satisfies A minus lambda I into V is equal to 0. Right hand side equal to 0 means this is a homogeneous system of equations, in fact linear equations. By solving these equations we get the corresponding eigenvector for each eigenvalue. Say let us simplify this using some example. Consider the matrix A equal to 4, minus 2, 1, 1. Let us find the eigenvalues. Eigenvalues are calculated by using determinant of A minus lambda I and equate to 0. How will you get this matrix A minus lambda I? From the diagonal elements subtract lambda, that is 4 minus lambda, this minus 2, 1 as it is, next diagonal element is 1, from this subtract lambda, so 1 minus lambda. So determinant of this you find it and equate to 0, we get the second degree equation which is lambda square minus 5 lambda plus 6 equal to 0. We know that there are two roots, lambda 1 equal to 2, lambda 2 equal to 3 for this equation. These two are called eigenvalues for the given matrix. At each eigenvalue we find the corresponding eigenvector. At lambda 1 equal to 2, how to find the eigenvector? Consider A minus lambda I into the matrix V equal to 0, where you substitute lambda equal to 2 in this equation. So we get this matrix multiplied with V, that is x comma y is the eigenvector, equal to 0. So there are two equations. If you solve this, 2x minus 2y equal to 0, this is the first equation, x minus y equal to 0, second equation. From first equation if you take 2 common, this also can be written as x minus y equal to 0. So there is only one equation, x minus y equal to 0, which is x equal to y. Say we don't know what are the values of x and y, let it be k. So the values of x and y are k comma k. So if you take k outside common, we get 1 comma 1. So 1 and 1 are the eigenvector corresponding to the eigenvalue lambda equal to 2. Right. Now we find the eigenvector corresponding to another eigenvalue lambda equal to 3. So again substitute lambda equal to 3 in this equation, we get this matrix multiplied by V, x and y equal to 0. Again if we simplify these two matrices, we get two system of equations. Say 1 into x minus 2y equal to 0, same x minus 2y equal to 0. So from these two we get only one equation which is given by x equal to 2y. So if we write any variable either x or y, if you assume k, suppose if you assume y is equal to k, then x is equal to 2k. So how will you get the eigenvector? X and y, x value as 2k, y value as k. So if you take k outside, we get 2 and 1. So this is another eigenvector corresponding to lambda equal to 3. So there are two eigenvalues 2 and 3 for which we find two eigenvectors, right? Now let us see few properties of eigenvalues. First property, sum of eigenvalues is equal to trace of the matrix. See, for any matrix of order n by n, the sum of eigenvalues is equal to sum of its diagonal elements. Trace is nothing but sum of the diagonal elements, which is called as trace. It is denoted by sigma lambda equal to trace of A, right? So let us see one example. If A equal to 4, 2, 1, 3. What is the trace? Add the diagonal elements, we get 7. This is trace. Now we have to find the eigenvalues of this matrix and add them, we have to get the trace. So there are two eigenvalues 5 and 2 of this matrix. If you add 5 plus 2, we get 7. So trace of A is nothing but sum of eigenvalues. Sum of eigenvalues. For any matrix, not only this matrix, any matrix, this property holds good. If you add all the diagonal elements, that is trace of A, that should be equal to sum of eigenvalues. This is one property. Now coming to second one, the product of eigenvalues is equal to determinant of the matrix. So for any given matrix, you know how to find the determinant and find the eigenvalues. If you product all the eigenvalues, that should be equal to determinant. Say for example, A equal to 4, 2, 1, 3 is the matrix. What is the determinant of this matrix? Is 10. So there are two eigenvalues of this 5 and 2. If you multiply these two eigenvalues, we get 10, which is same as its determinant. So this is also one of the property. Some product of eigenvalues is equal to determinant. Coming to another next property, eigenvalues of inverse matrix. If A is invertible, invertible means inverse exists, and eigenvalues of A inverse are nothing but the reciprocals of eigenvalues of A. Say for example, if for any matrix A, if the eigenvalues are 2 and 5, what will be the eigenvalues of its inverse? A inverse means you just take the reciprocals of this, that is 1 by 2 and 1 by 5 are the eigenvalues of A inverse. This is one property. Coming to another property, eigenvalues of a scalar multiple of a matrix. See, if capital A is a matrix and it has eigenvalues, say lambda 1, lambda 2 and so on, lambda n, then for any scalar C, this property holds good. Lambda into Ca equal to C into lambda A. Say for example, if A is any matrix which has eigenvalues 3 and 4, right? 2A is any matrix which has eigenvalues, you multiply these with 2. So 2 into 3 is 6 and 2 into 4 is 8. So where C is a scalar multiple, here 2 is a multiple, right? Another property, eigenvalues of a transposed matrix. The eigenvalues of A transpose are the same as eigenvalues of A. Transpose means if we interchange the rows and columns. For the given matrix, if we interchange rows and columns, then the eigenvalues will remain same. Suppose if this is a matrix 4, 2, 1, 3, this already we have seen the eigenvalues of this matrix are 5 and 2. If you interchange rows and columns, still the eigenvalues remain same, it won't change. Next property, eigenvalues of diagonal matrix. For any diagonal matrix, the eigenvalues are simply the diagonal elements. Diagonal matrix means except the diagonal elements, all other elements are 0. So these are the principal diagonal elements, remaining all elements are zeros. So only whatever the elements are available in the diagonal elements, those those are the eigenvalues, right? Next property, eigenvalues in upper triangular or lower triangular matrix. For any matrix, whether it is upper triangular or lower triangular matrix, the eigenvalues are the diagonal elements. Not even for diagonal matrix, upper triangular or lower triangular also. Say for example, A equal to 3, 4, 5, 0, 6, 7, 0, 0, 8. You can see all the below diagonal elements are 0. So this is upper triangular matrix. So whatever the diagonal elements are there, simply without any solving, we can say that the diagonal elements are its eigenvalues, right? Next property, if A is orthogonal and eigenvalues have absolute value 1. For any orthogonal matrix, the eigenvalues are nothing but its absolute value. For example, A is given like this. The eigenvalues are its complex numbers e power I theta and e power minus I theta, which have the magnitude 1. So, e power I theta means modulus of cos theta plus I sin theta. So, this is under root of cos square theta plus sin square theta, which is equal to 1. Similarly, magnitude of e power minus I theta is also 1. So, these are the properties of eigenvalues. So, today we have, in this lecture we discussed what are the eigenvalues and eigenvectors and properties of eigenvalues. Next class we have seen in the next lecture the more in detail problems on eigenvalues and how to find the eigenvectors.